let's talk about one of the interesting topic in the group theory, that is the cosets, right? So let us consider, G a set, a group. So G is a group, and now let me say that H is a subset of G. So for H, like any subset which is non-empty, so I define this set AH, which is containing the elements which are like multiplied, I shouldn't say multiplied, which are which are found by the binary operation of A and all the elements from H, right? So this is H, and we also define HA, that is of this form, right? So whenever this H is a subgroup, whenever this H is subgroup, in this case AH is called left coset of H in G containing A. Why does this contain A? Because H is a subgroup. So when H is subgroup, it contains identity. When A is binary multiplied or taken in binary operation with E, then AE becomes A, because H is subgroup. So E belongs to this, so A belongs to this AH. So like when H is subgroup, A belongs to H, right? This AH is called the left coset, while this HA is called the right coset of H in G containing A. By similar argument, you can say that why the hell this A is inside this HA. Additionally, this A is called the coset representative of AH. So this element A is basically coset representative of H, right? So whether it is in the left or in the right, so it doesn't matter at all. And what does this guy show? So AH represents the number of elements inside H, and HA also denotes the number of elements inside A. So like you take this order of AH or HA. So let's move ahead. Let's take an example. So we take an example. This example, I'll take an easier example. Let's consider this Z9. So this contains 0, 1, 2, 3, 4, 5, 6, 7, 8. Right now I am interested in finding out the left and right, so like left cosets of this set, which is 0, 3, and 6, right? So what are the left cosets of this? So if I take 0 plus H, so it is going to be 0 to be added with each element of this H. So 0 is added into 0, it becomes 0. When 0 is added with 3, it becomes 3, and then 6. So like it's fine. When 1 is added into H, so here the addition is modular addition, A mod M, like so, modulo n. So when I add 1 with 0, it becomes 1. When we add 1 with 3, it becomes 4. When we add 1 with 6, it becomes 7. And when I add 2 with H, it becomes 2, 5, and 8. But interestingly, when you add 3 with H, it becomes 0, 6, and when you add 3 with this, my mistake. So when you add 3 into 0, it becomes 3. When you add 3 with 3, it becomes 6. And when you add 3 with 9, of like 6, it becomes 9. And 9 mod 9 is 9 mod 9 is 0, so it becomes 0, right? So you can see that these sets are similar. So 4 plus H will become 4, 7, and then when you add 4 with 6, it becomes 10. And 10 mod 9 is 1, so it is 1, right? So these sets are also similar, and this way 5 plus h will become 5, 8, and 6 plus 5 is 11, and when you take 11 mod 9, it becomes 2. And similarly you can take now, like if I take 6 plus h, so it will be 0, 9. So 9, obviously 6, 0. So 0 plus 6 is 0, and 0 plus 3 is 9, which is 0, and 6 plus 6 is 12. So when you take the modular with the 12, it becomes 3. So like when this is done, so like this set is again similar to this, and similarly 7 plus h will be 7 and 1, and then like it's 4. And when you take h, 8 plus h, it will become 8, 2, and 5. So these are similar. So this is how you find out the cosets. Like in this case, you can see how we have found out the cosets. We'll be looking into these results. So if h is a subgroup of G, then you can show that A belongs to H is H if and only if A is inside H, and 3, 4, all of these properties. So let's talk about the one, why this one is true. So why this is true? Why this one makes sense whenever H, so like we have assumed that H is a group, and H is a subgroup, and A and B belongs to G. So like we need to keep and add the assumptions, right? Because if we don't care about the assumptions, then we can face trouble, right? So let's talk about this, right? So we have to show why this A is inside AH. Sorry. So obviously, because I can write this because E belongs to H. So when you will be taking the binary operations of A and H, when there will be when there will be the round of E, so you will take A with E binary operation, then you will get A. So because this guy is inside AH, so this has to be inside H. So that's very simple. Now next is this. So the second is, it says that if AH is H, then you have A inside H, and when A is inside H, you have AH equal to H. So it's a two-way implication. Let me assume this, let's assume, assume that AH is same as H. Now let's because AH is equal to H, and we have seen from the property 1 that A is always inside AH. So and AH is equal to H, so this implies A is inside H. So because A is always inside this, so and this set is equal to this, so A will be inside this, and you will be done. What is going to be the, let's see what is going to be the argument for the other side. Now we assume this, now we are in the reverse direction. So now we assume that if A is inside H, then I can show that AH and H are same. So what we need to develop is AH is sitting inside H and H is sitting inside AH, right? So let me pick an element from here. Let X be an element from AH. So this implies X equal to A times H for some H inside H. But now you can see that A is already inside H from the assumption, and H is also inside H, and H is a subgroup. So these both elements are in, from the H. So H is a subgroup, so AH must be inside H, and this implies that X is inside H, right? So this inclusion is fine. Let me pick an element from H, right? But I'm already given this assumption that A is also inside H. Now H is a subgroup. So, first step, one step criterion for proving the subgroups. You remember, if two elements are from H, then one multiplied with the inverse of the other must be inside the group. So in other words, A inverse H must be inside H, right? So you can explore this, right? Now what I can do, I can write this guy H as identity times H, but this identity can be written as A times A inverse H. Now you already have seen that this guy is inside H and A is also inside H. So okay, so like this guy is inside H and A is multiplied with his. So this is some element A H bar, where H prime is an H. So this is a form of element of A and subgroup H. So H is in this form, so I must have, H belongs to AH, right? I'm sure this makes sense. Let's do the third property. You say that AB and multiplied with H is same as, so like taken as a coset, AB coset H, which is same as, and also H with AB equal to HA with B. Now why this is fine. So it's a third property. Now like you can easily see that it is nothing but the transitive property. So I know that AB times H, because all of three elements are from G. Because if A and B are from, A and B are from G. So A and B are from G, and H is from H. So, but H is a subgroup of G. So technically, all of these three elements are from G, and G is a group. So, like transitivity implies that what should I say? So this, and this is a typical form of element from these sets, so you can conclude, and similar argument can be written for this. It follows from the transitivity. Or even if you take the elements and then apply, for example, if you take y from this a b h, then y must be in the form a b h, but a b and h are from G, so G is a group. So by transitivity I have this, and this is nothing but an element of BH, so y must be inside BH, right? So you can simply write the argument if you follow this again for both. It's not that much difficult. It's just the consequence of transitivity of groups. Fourth property is this: if AH is same as BH, then it implies that A belongs to BH, right? So A belongs to BH, and if A belongs to BH, then AH and BH are similar. So let's write the proof for this, right? So property 1, recall property 1, see it. It says A always sits inside AH, and we have been given, so like I'm in the forward direction, I'm assuming this is true, I have to prove this. So because A is inside H, and we have seen so it's in the first property, and AH is same as BH, so this shows me that A should be inside BH. Now there will be, now we will consider, or we will assume that A is sitting inside BH, and then we will prove that AH and BH. Now if A is inside BH, then A can be written as B times H, where H is an element from H, right? Now you consider this side, so AH can be written as BH H, right? But this can be written as B times HH. Now second property is invoked, which says that if element A is inside H, then element X is inside H, then XH is same as H. So if element is from H, then its coset is going to be equal to H. So this is H, and this way property 4 gets finished. So next we will be turning towards the property number 5. So property number 5 says that, so property number 5 is telling us that AH is equal to BH. So either AH is equal to BH or their intersection is empty. So AH intersection with BH is empty. So either both are equal or their intersection is empty. So if both are not equal, then their intersection is going to be empty, and if the intersection is not empty, so I'll prove it in this way. I'll say that this is not phi, then I'll conclude that this is phi. So I'll shut this false, and then I'll see that this holds. So let's assume that C is inside this intersection AH intersection BH. So this implies C is sitting inside H and also C is sitting inside BH. So it's AND, right? Now we have seen in the property number 4 that if an element is inside, like this was the property number 4 I'm saying here. It says that xy is yx or xh is yh if and only if x is inside yh. So if x is inside yh, then the left coset formed with the help of x is same as yh. So because C is inside this, so this implies left coset formed with ch is same as ah. And similar argument gives, so property 4 is invoked. So ch is same as bh, property 4 that we just did. So this implies that ah is same as bh. So like if the intersection is not empty, if there is a single element common between two left cosets, then both of the sets are going to be entirely equal. Right? So it is very interesting. It says that if you have got a left coset xh and you have got a left coset yh and you found out an element inside both, then they are going to be equal. Wow, that's really interesting, right? So, and the next property is 6 number, and property number 6 states that, okay, so it says what? It says H is BH, AH is BH if and only if A inverse B is inside H, right? So we will prove this. Okay, proof. Let's assume that AH and is same as BH, right? So our task is to establish this. A inverse B is inside H. This is what that we will develop. So from here it is obvious that AH is equal to B times H prime for some H and H bar inside H, right? So like from here I can write H equal to A inverse B H prime. So now this element H is inside H, right? One thing can be seen, that this H and H prime are both inside H, and H is a subgroup. So I can take the inverse of this guy, then A inverse B H. Now this element is inside H. So this shows that A inverse B is inside H. If you have any query regarding this, you can ask in the comment section. We can discuss. The next is assuming this A inverse B inside H and showing that AH is same as BH. We will show this, right? Okay, the property number 2. Property number 2 says that if an element X is inside H, then this implies that XH is same as H, right? So like if I take this whole element as X and X is inside H, so like let's say that this is X, so my XH must be H. In other words, I will write A inverse B multiplied with, taken as a quote says, with H is equal to H. Now you just take A on both sides as coset for this, and then you just apply some operational properties. So you are taking product with a on both sides, so multiplication or binary operation. So this will give me bh equal to ah after careful deductions. Next is the property number 7, and it says that order of ah is same as order of bh for in fact it is going to be equal to h, because a b are inside g, so e is also inside g, and we know that eg is h. So like if you know the order of h, then you know the order of all of its cosets, and this is going to be consequent somewhere, we will see later on as well. So yeah, order of h. So how can we prove this? So one of the interesting thing would be to define isomorphism between them. So I'll define the isomorphism as phi ah equal to bh, right? Or you can say that 1-1 correspondence, so 1-1 and onto. It's not a difficult job to see that this is 1-1 and this is onto. Why this is 1-1? So why this is 1-1, right? Okay, so like if I take phi of ah equal to a1h equal to phi of a2h, then this is going to be equal to, so how can you must have written this ah1 and ah2, so this implies bh1 and this is bh2, right? And this implies h1 is h2, and you again take multiplication with a. So like if x and y are phi of x is equal to phi of y, then x is y. And you can also see that this is a 1-to-1 correspondence, so like this order of these these sets remains the same. Now we have got the property number 8, and it says that if you have ah equal to ha, but this implies that h is same as a inverse, and reverse is also true. But this is very interesting for the normal groups, so we will use this when we will be talking about the normal subgroups, sorry. Now I assume one side, and I'll prove this other side. Let's assume this is true. I think this side is trivial. If ah is same as ha, you just take the inverse multiplied, and oh, sorry, my bad. It will not be okay. So like what I can do with it is I take the a inverse on this side. So okay, now it is fine. Now this will become a inverse equal to h. I think this is fine. How this implies this and this implied this, and you can go backward as well, just reverse the steps. The property number 9, and of course it is the last property, says that ah is a subgroup. Ah is a subgroup, so I write subgroup like this. Ah is a subgroup if and only if a is inside h. So if a is inside h, then ah becomes subgroup, and if ah is subgroup, then a has to be inside h. Now let's prove. So like we are proving the property number 9. Okay, so let's assume h is a subgroup. So proof follows this way. Assume ah is subgroup. Our task is to show that a is inside h, right? Now if ah is a subgroup, then e must be inside h. Now property number 2 says that if x is inside no, not property 2, is property 4. It says if x is inside yh, then this implies that xh and yh are same if and only if. Now because ah is a subgroup, the identity element must be inside this, so this implies that eh is same as ah, and this shows that eh taken intersection with AH must not be empty, right? So there are common elements, right? And we have also seen previously that, but I think here we are also done, because identity time H is H. So identity times H is H. So like, if even if we don't see this, then we have this EH equal to AH, so which is H. So H is AH, and now you can utilize the property number 2, which says that AH is H if and only if H is inside A. So this implies H is inside A, right? We are done. Next is, okay, so the next is, assuming this, that A is inside H, and we will establish that AH is a subgroup, right? And we can apply property 2, because if H is inside A is inside H, then AH is same as H, and we have assumed in the start that H is a subgroup, so hence AH is a subgroup. AH is a subgroup.